So today we will start with the family of techniques that are based on the gradient function. So just a reminder, we are minimizing, let me see here. So that we this one. So we are minimizing the function for some constraints. Some of them are inequalities, some others are equalities. So let's look at this function f. So we will use the gradient of f. So if f is two-dimensional function, then this surface is xy and f of xy. And then the gradient is a vector that points in the direction in which the function is growing maximally steep. So it is a maximum slope that you can have in the function and in the direction that it grows. So gradient descent is the opposite. So instead of going in the direction that it maximally grows, we will go in the opposite direction. So we will subtract the gradient from the point from xy, so that we go in the direction that it goes, that the slope is maximum, but in the opposite direction, going down rather than going up. So a reminder of what the gradient is. So let's say that we have a function, some vector f. So the gradient of this, so the gradient with respect to x is a vector that is the partial of f with respect to x1, the partial of f with respect to x2, partial of f with respect to xp. And this has to be evaluated at some point. It is the same point as here. So these 2 points are the same. So this is the definition of gradient. And then, yeah. Very good. So let's go, wow, this one. So you see, what I have just explained with words is the basic of the gradient descent algorithm. So in the unconstrained case, so for the moment we are forgetting about the constraints. So you have a current point, you evaluate the gradient at that point, and then you go in the opposite direction. And this alpha k is how much you go into that direction, because you can move just a little, or you can move a lot in that direction. So this is controlled by alpha k, and that will give you a new point, and then you iterate it again and again. And this alpha k is called the step size or the learning rate. And if you don't have explicit gradients, so you can compute analytically the gradient, or you can compute it numerically. So to compute it numerically, what you do is you are at a point. So this x is this x here. So it is a vector. And then you perturb it a bit, and this bit is a small step size h, and you do this perturbation in each component. So you do it for the first component, second component, third component, up to the p component, as I have shown in the whiteboard. And then you perturb it a bit up, you perturb it a bit down, you compute the difference between these two, and you divide by the length of that. So that is approximating the function by a line and computing the slope of that line. Yeah, this EI is a unit vector in the ith direction. So it is all zeros except a 1 at the position I. And then you approximate the gradient by these kind of derivatives. These kind of derivatives, they are called the central difference formula. And it says it is most accurate. You can have even more accurate approximations, but you have to measure more points. But with only 2 points, this is the most accurate. And then you do those perturbations for all the components in the vector X. Okay, so it is a very simple approach. And here you have the code to do that. So here you have the inner or the loop over all positions. So you start with some X naught, and then we will keep a history of that. And then you can, this is interesting. So this function can receive the gradient, so analytical gradient, or not. If it is the analytical gradient, you take it. But it is, if you're not given the analytical gradient, then you compute the numerical gradient as we have said. So you go for all components of X, you perturb it a bit, perturbation up, perturbation down. You evaluate the function at the 2 places and divide by 2h. And then you have the gradient. You can compute the norm of the gradient. If it is smaller than something, you stop. Because if the gradient is too flat, that means that you have gone to a point where you will not move anymore. So actually, you know that at the minimum or at the maximum, the gradient is 0, and in the saddle points too. So either you are in a saddle point or in an optimum. So you stop. Otherwise, you move into the direction of the gradient, opposite direction. This is this minus, and you move this step side. So this is a very simple implementation of this algorithm. Actually, for your practice, this part, I think it is more prone to do this kind of implementations rather than to optimize a specific function. Then, how much you move along this direction. So this applies in general, not only for the gradient. So this decay will be the direction that we will be exploring during your optimization. And for the gradient descent is the gradient, or the opposite of the gradient. But in general, it can be any other thing, any other direction. We will see actually some examples in which decay is not the gradient direction. It is somehow related to it, but it is not exactly the gradient. Okay, so let's say that we are minimizing. So you have to move along a line. So you have computed the gradient here. So this line, and then the question is how much I should move along this line. And that movement and that minimization is a 1D problem. So the full problem is 2D. But moving along the line is a 1D problem. So now what I have to find is the best alpha k larger than 0, such that these functions along this line is minimized. So probably in this example here, you would stop somewhere there, because along this line, it is the minimum that you can find. So this is moving too little. You could get much further minimization if you move up to this point. And the problem with this is that, so this method is called the exact line search. Somehow this is trying to represent that. So let's say that this is your function, this is your gradient, and then the thing is how much I should move. If I move a lot, then I could go down quite a lot the function. If I move very little, I don't move so much along the function. Actually, all this is called the interval of admissible step sizes. So down to here, you are minimizing. Beyond that point, you are away from the minimum. Okay, and it is rather precise, but it is closely, and sometimes it requires many evaluations in one dimension, which are cheaper. But still, you may have many evaluations. And then there are some kind of shortcuts that. So these shortcuts, they are willing. Okay, it will not be the minimum along the line, so it will not be the best point that I can have along this line, but it is sufficiently good. And sufficiently good has to be defined somehow. Okay, so I will be moving alpha, and then what I'm requesting from this alpha is that the evaluation of the function after my movement is whatever I had at the beginning, plus something that depends on the derivative and the direction that I'm looking. Okay, so this is the gradient, and then I'm moving in the direction decay. And then here you see this is kind of linear approximation of the function. So it is kind of doing a linear approximation of the function and trying to make sure that you are below that thing. So here, somehow, if our function is this one, and this is our gradient somehow, so you are moving along this line, and then all these points are admissible because they are increasing. So this line alpha is this line. So at the point you are, you draw a line, and any point that is below that line is admissible. Okay, so that is what that condition is saying. And this C1 is something that you fix. So it is not something that is computed by the algorithm, that the user has to say, what is this C1? And this is called the Armillo condition. Here you have the Wolf condition. So the Wolf conditions is somehow a little bit stronger. Now you will have two components, and somehow these are related. This is approximated by a line. This is taking account the curvature of the point of the curve at the original location, at the escape location. So you have now to define C1 and C2 such that this is fulfilled. Okay, very good. Any question? No? Then there is something that we can do, that is trying to smooth the steps that or the trajectories that we follow with the gradient descent. So let's say that you have to minimize this function, and then minimizing this function, sometimes in gradient descent you start doing this zigzags, and zigzagging probably is not the most efficient way to get to the minimum, because you have to evaluate the function many times. So you have to evaluate it here 1, 2, 3 times, 4, 5, 6, 7, so on. So maybe if you move in a more straight line to the minimum, you will evaluate the function fewer times. So that is what this adaptive step size is trying to do. And this adaptive step size, you see, the formula is very similar to the one of gradient descent. So except for this term, it is exactly the gradient descent. Actually, if you remove the denominator, it is gradient descent. So it is gradient descent in which you will make larger steps if the gradient norm is small. So what you will do is you will keep a track, a kind of moving window along what is the gradient norm at each one of the points. So if the gradient is small, then you will move further. If the gradient is too large, so it is very small, then you will move just a little bit. And this is kept track with this expectation of the norm of the gradient. So it is a moving window. So this moving window is or it is a smoothing kernel, if you want. So you start with the gradient. The first one will be 0, so the expected value of the gradient will be 0. So what you will do is, and this row is a parameter kind of 0.9. Okay? So here you have 0.9. So you will update what is your gradient norm. So you compute the gradient norm multiply by 0.1, and this is 0 the first time, and then this is your expected norm of the gradient. And you hope that, or you expect the gradient to be relatively small because it is only 0.1 times the true norm. And then you will make a larger step. Somehow this is more represented here. Okay, so the first step is larger. Yeah, alpha is the learning rate. It is the same as in gradient descent. This is the same as in gradient descent. We have gradient descent, we have it here. Okay, so it is the same there. And what else? Yeah, and we have some epsilon just to avoid dividing by 0. So let's say that our gradient is all the time constant. The norm of the gradient is all the time constant. So let's say that over k, so over the, this will be the norm of the gradient. And we have called it in the slides, we have called it g squared. So let's say that it is constant, but we started with 0. So now we will represent the expected value of g squared. So we started with 0. Let's say that the norm of the gradient is all the time constant, then this will grow something like that. And how fast it grows depends. So this is proportional to, how we call it, rho, I think, no? It's rho. So it is proportional to rho. So let's say that you have a very small rho. So you make very little updates. So if you make very little updates, it will go very smoothly through that one. If you make very big updates, you will go very quickly. But very quickly, you probably foresee that it can be unstable, and then you might have the same problems of zigzagging as you had there. Okay, so this adaptive step size method is called RMS prop. Actually, it is one of the ones that they are very much used in neural networks. So when you train a neural network, the norm of the gradient with respect to the weights, they are kept internally, and then it is updated this way. Very good. Then we had constraints. So how do we handle the constraints? So first we do a kind of a gradient descent step. So you are at xk, then you update, you produce, let's call it yk. And then this yk is projected into the feasible set. So this is the projection operator onto the feasible set. Okay, and so the gradient descent, you move to here. So let's say that this is your initial point. So with the gradient descent, you move to here, and then you project, and then you move to here, then you project, you move to here, you project. Okay. So it is a mixture, alternating mixture between gradient descent and projections onto the feasible set. We say here that it works well if projecting is easy. So for instance, let's say that your constraint is an Euclidean ball. So it is the norm of x is smaller than I. So that is this ball here. Let's do it in two dimensions, but we can draw easily. So this is our x plane, and this is our ball. So that's my result. And you are at a given point here. So this is your current, let's say, x0. How do we project this into this ball? So you would join by a line and compute so you have to move along this line, reaching this point. So you look at the formula, that is exactly what it is down. So y divided by the norm of y is the line, and then multiplied by r is the one that reaches the border of the ball. And that is if you are outside the ball. If you are inside the ball, you don't touch it. So sometimes it is easy to project, some other times it is not that easy. Okay, then we had constraints that were inequalities and equalities. So a different family of methods to handle these constraint problems is this penalty method. So these penalty methods will include the how far you are from the equality or whether you are violating the inequality or not. So we will be put as a constraint, so as a penalization. And then you have this penalization parameter, mu, that controls the strength of the penalty, So as you want to minimize something, this is always a positive number. This is always a positive number. So you will try these two positive numbers to be zero, such that you are compliant with the constraints, but still you are minimizing your function. Okay, so this is these are called the penalty method. So you can see that the way to handle the constraints are different. So here we forget about the constraints and then we project. And here, when you compute the gradient of this thing, so now when you are computing the gradient with respect to x, it is the gradient of the whole goal function. It's not just f. So it is the whole goal function. And this gradient here, so you see the differences between equalities. So in equality, if you are equal, so let's say that x evaluated in this HEA, it is zero. So you are exactly at the line or at the curve. Then this will be zero and you are not penalizing at all. As long as you deviate in any way from the line, you will be penalized. Okay, what about this one? These are the inequality constraints. So the inequality constraints, let's say that we have here G1 of X. Actually, this line, the line is G1 of X equals 0. And then you are constraining to G1 of X smaller 0. So that's it. That is our constraint, smaller or equal 0. So let's say that you are already fulfilling the constraint. So you are here. Okay, so it will be the maximum. So it will be the maximum between 0 and GI. But GI is a smaller or equal 0 because we have said in this region, this is a smaller or equal 0. So at this point, it will be smaller or equal 0. So it is the maximum between 0 and a negative number. So it will be 0. So you are not penalizing. In this other side, I don't know which color to use. But in this other side, G1 of X is larger than 0. So now you have, if your red point is in this region, then this will be a positive number. It will be the maximum between 0 and a positive number. So it will be the positive number. So we see that this is actually constraining the X to be on the side where it is not penalized. So the problem now it is easier because it is unconstrained, but this mu may be hard to tune. So how should we how should we set the strength of the penalty so that it doesn't freeze at the beginning, the minimization. Sometimes if you put it too high, it doesn't know in which direction to move because everything, all the landscape seems very high, very flat, and it doesn't know where to go. And here you have a different family of methods. So this is only for constraints, inequality constraints. These are called the barrier methods. So the barrier methods somehow bring the same idea of penalization, but with a particular kind of penalization. So you have to start with a point that is fulfilling the constraints. So let's say that this is our feasible region. We have a lot of constraints here. In this problem, we want to maximize x1 plus x2 subject to a number of constraints, and this p takes value 0, 0.1, 0.2, up to 1. So we have many constraints, the ones we have drawn there. And you have to start with a point that is already fulfilling all those constraints. Those are called the interior point method. So you have to start from a point that is in the feasible region. Okay, so you start somewhere here in the feasible region, and then you want to minimize your function. And then these logarithmic penalties, they force the point when they get to the barrier, when they get to the boundary of your constraint, they get very high. The logarithm grows to infinity very quickly. So those are regions that the x point cannot cross in this gradient descent approach. Okay, so this is another way of putting these constraints. Any question? Okay, so then we have these Lagrangian methods and Karuskun-Tucker methods. So we have the Lagrangian of the function. So the Lagrangian is the goal function plus all the constraints. And then you apply the gradient descent on the primal. So the primal variables are x. So you compute the gradient descent on x. And the dual variables are lambda and nu. So you apply gradient descent, but now your variables are x and lambda and nu. And these are a family of methods that are called also primal dual methods. And this primal dual methods is somehow a generalization of the gradient descent, because gradient descent only cares about the x. Here now you care about x and lambda and nu. Any question? Very good. Then all these methods, somehow the gradient descent, somehow they are based on, many things are based on a Taylor expansion. So the gradient descent, somehow you see that it is somehow related to the first order expansion, Taylor expansion of the function. So if you have a point, xk, and xk plus a perturbation, so and this perturbation is small, then if you want to expand the function around that point, that will be the function at xk plus something that depends on the perturbation size and the gradient. And the gradient descent would stop there. So somehow all the methods we have seen, they are based on a linear approximation of the function. And what if we include the second order term of the Taylor expansion? Now we have here the Hessian. So this second derivative is called the Hessian. And the Hessian is something like this. So now it is a matrix. the Hessian of a function, it is a matrix that is the first derivative of A with respect to x1 and x1, second derivative, sorry. And then second derivative of A with respect to, never remember the order, it is one or the other. Let's say it is this one. And here we would have second derivative. It is this matrix. So this matrix somehow is encoding what is called the curvature of the function. So if this is you have to evaluate this at a given point. So all these derivatives have to be evaluated at that point. And somehow the eigenvalues of that function encodes how flat or how curved it is the function around that point. It is the eigenvalues of the function. Okay, so then we can learn about the curvature of that. And then what we can try is, okay, so I will look for the perturbation that minimizes the second part of this Taylor expansion. So I'm looking for it. So it is whatever it was plus something. So what if I minimize this something, then I will be minimizing the function around that point. So let's look for the minimum of that thing. And the minimum of that thing with respect to P. So we are minimizing with respect to P. So now we have to compute the gradient of this with respect to P. So with respect to P, this is a constant. Okay, and the derivative of a constant is just there. So it is. Do you remember in the first lectures we introduced the vector calculus and the matrix calculus? So derivative of this, derivative of this derivative with respect where this is a vector of A transpose X is A. That is the, so it is one of these rules, differentiation rules that we saw at the beginning. So this will be this gradient, and then there is another rule, and the derivative of P transpose a matrix, but this matrix is a constant with respect to P times P is it's this one. It is just the matrix times P. And now you can solve for this very easily because you don't have only pk here. So pk is the inverse of this matrix times the gradient. Okay. Very good. So now we have the best direction in which we should move and by how much. So what we are doing is this kind of stuff. So let's say I have done it in one dimension because it is easier to draw. But let's say that we have this function, pink. So the first order Taylor approximation is this one. This is the kind of approximations that gradient descent is working on. And the second order approximation is okay. So around this point, I am approximating by a parabola, and then I will try to look for the minimum of the parabola. So this is what we are trying to do. Okay, and we have already computed what is the best direction and how much we should move into that direction. That was this thing. And you see here there is no learning rate. So you can compare to the gradient descent. So gradient descent actually looks very much like this one. So it is same direction, but in gradient descent you are plainly following that direction. In the Newton iteration, you are modifying that direction by a matrix. And here, how much you were moving was fixed. Here it is given by that inverse of the Hessian. And if you think of the inverse of a matrix, the eigenvalues of the inverse have to do with the eigenvalues of the original matrix. So somehow this Newton method is incorporating the curvature. So I told you at the beginning, the curvature is related to the eigenvalues of the matrix. So you are including those curvature measures into how much you should move. Yeah, and Newton's method accounts for the curvature, so it gives quadratic convergence. Quadratic convergence, you have linear convergence for the gradient descent and quadratic convergence for the Newton's method. So that means you will go twice as fast if you want. But there is a problem. You have to invert this matrix, and inverting the matrix is not cheap. So depending on how large your matrix is. So for instance, for neural networks, you can imagine that this is quite large, so you cannot minimize it very easily. Invert it very easily. Okay, so then there are approximations to that. So these are BFGS method. BFGS stands for the names of the people who developed the method. So instead of inverting the Hessian matrix, we will construct an approximation to that matrix. And you need the gradient or an approximation of the gradient. And then you proceed in this way. So let's see. So let's say that the first estimate of the gradient of the Hessian, let's say it is identity. You start with identity. Okay. Then you compute the gradient, you multiply by your current estimate of the Hessian, not the Hessian, the inverse of the Hessian. You see, H is the inverse of the Hessian. So you multiply by this, you have your direction to do minimization. Then you do a line search along that direction, and you update your position. Okay, and now you define two vectors. The two vectors will be how much you have moved, and the other one will be how the gradient has changed. So you evaluate the gradient at k, you evaluate the gradient at k plus 1, and how much the gradient has changed. And then you update your inverse of the Hessian in this way. So the inverse of the Hessian is whatever you had before, plus something that depends on how much you have moved in x, how much the gradient has changed. Here you have the same. And here you have how much, somehow it is the norm of how much this thing has moved. And then this rho k is this calculation. So you see that everything is relatively well known. So xk is your current point. You can evaluate the gradients. That is one of the requirements of the algorithm, that you can compute the gradients of your function. But then if you can compute gradients of your function, you can iterate, and you don't need to invert the Hessian of it. So you don't need to estimate what is the Hessian. So you don't need to calculate the second derivatives. So you will be approaching to the inverse of the true Hessian as you iterate. Any question? Okay, more algorithms in this family. These are called the momentum-based algorithms. So we start from the basic gradient descent, and then the basic gradient descent may have a problem. that is something close illustrated here in this figure, that it can do zigzags. Okay, so why don't I, if I think, let's say that I think of this minimization as a physical problem. So let's say that there is a mountain that I'm going down, and I have a ball with some mass, and this mass starts moving. So probably it cannot make this kind of movements, zigzag movements, because it has some inertia. So inertia means that the transitions have to be smooth. So this inertia is encoded somehow in the velocity of the ball. So if this ball is falling, so it has some velocity, and the velocity has to change smoothly. So that is what we will do. So see here. So we will update our position according to our velocity, and the velocity will be calculated using the gradient. So you see, it's again kind of a smoothing between how much important is the previous velocity. So this gamma and this gamma phase values typically 0.9 instance, and this eta. This eta is the learning rate, and you may choose it to be 1 minus gamma if you want, but you are also free to put anything else. So it is how much more important is the current gradient with respect to the previous velocity. And then what you update your position is with the velocity. And this momentum, actually, it is very good for saddle points. So if you think of a saddle point is a point in which the function gets very flat. So let's say this is our axis, this is our function, and we are falling from here. So here we have a good speed, and then at some point we get to that location. So just with the gradient, we cannot move because the gradient doesn't change there. But you have some velocity. So if you have some velocity, still you will keep moving in this direction, and at some point you will get away from the saddle point. So these are very good for getting away from saddle points, and again they are very much used. Actually, the Adam, have you heard of this method for neural networks? Adam is currently, I'd say, one of the standards to minimize the weights in neural networks, and the M in Adam is for momentum, and the ADA is adaptive. So somehow it is a mixture. We will see, the course we will see that. But it is a mixture between, what was it? RMS probe. No, it's before. So it is a mixture somehow between this RMS probe, in which the steps are adaptive, and this momentum idea. Okay. Now, next, another method that is very, very famous is conjugate gradient. So conjugate gradient has to do with the gradient, but again, what we are trying is to get away from this zigzagging behavior of the gradient. So we will, in conjugate gradient, we will try to get just in 2 steps to the minimum. Okay. So 2 steps if this is a quadratic form. If it is any form, then it would take more steps. Okay, let's see. So let's say that we want to minimize this function. So this function, you recognize it is a quadratic term. It is a quadratic form. This quadratic form, you have a quadratic term and the linear term, and the 0 order term that you don't care because it is constant with respect to x. So you don't care about this one. So now you compute the gradient of this function. So the gradient is this one, and you set it to 0. Then minimizing this problem is the same as solving an equation a linear equation system. And there are some constraints. So if this is a quadratic form, for a quadratic form, A must be symmetric, positive, definite. So all the eigenvalues have to be larger than 0 or equal 0. No, larger than 0. So if they are 0, it would be semi-positive. And then what we will do is look for directions that are A conjugate. Okay, so two directions are A conjugate if this is fulfilled. Okay, so Pi transpose A, Pj is 0. So if this is true, then these two directions are A conjugate. And the idea is that you will look for some direction, and then the next one is not orthogonal to that. So the gradient descent, by definition, this one has to be orthogonal to the previous one. But this one doesn't need to be orthogonal, but A conjugate. So A conjugate in a 2D in a quadratic problem will go faster because you are not somehow undoing part of the gain that you had here. It was undone by this movement, and then you have to zigzag. But here you are moving in the direction that goes from where you are to the minimum. So this conjugate gradient directions ensures that each direction is independent in this sense, in the A sense, and non-redundant in terms of curvature. So the key idea is to look at the curvature of the function and then go in the best directions according to this curvature. There are some theorems that tell you that conjugate gradient converges at most in n steps. N is the number of variables at most. So it is a very, very fast algorithm. So how it is done? So we have to solve this equation system. So you start with some initial guess, whatever, for instance, 0. Then you compute the residuals, the current residuals, and that will give you the negative gradient. And then you have to look for the direction in which you will move. So this direction, for the beginning, it will be the gradient. It is our best current estimate. Okay, and then you will iterate. So the step size is calculated in this way. So the step size, you see, it is the norm of the residuals. If the residuals are small, then your step will be small. And then the norm of pk with respect to the matrix A. This is the norm pk in this matrix. And then you update your solution, you update your residuals, and you have to update the direction. So for updating the direction, you use this thing that everything is known. And then you update your direction. So this is what I told you. For your practice, I think it is easier to implement this kind of algorithms rather than I will minimize this function. This is not so interesting. Any question over here? No question? Okay, so let's make a break. Okay, so following with the gradient-based methods, some other families of method, they use what is called a pseudo gradient. So the pseudo gradient, the gradient is the direction in which the function decreases the most. But what if it doesn't decrease the most, right? It's sufficiently good. That is what these pseudo gradients algorithms try to look for. So we will not see any of these methods, but just introduce the idea that maybe you don't need the gradient you need the direction in which the function decreases. So in general, it can be explained here. So x minus a little movement in that direction is smaller than where you were. So this is sufficiently good. It is minimizing in some direction. Maybe not the best step that I could take. The best step is always the gradient, but still, if it is good enough, then I don't have to compute the gradient, which may be expensive or may not exist. For instance, you have some non-differentiable functions, or you have some functions that are very expensive to evaluate. Then these numerical gradients are expensive, or the gradient is stochastic because your sampling is random, or the function is expensive, and then you use this called surrogate models. So a surrogate model is somehow what we showed here. So this is a surrogate model. So let's say that the peak function is very expensive to evaluate. So every time you have to compute f of x, that takes a lot of time. So you compute a surrogate function that is sufficiently close. You can evaluate this surrogate function as many times as you like. And then once you have evaluated it, you have reached the minimum of the surrogate, then you go back to the original function to see if you have done well or bad. Okay, so there are situations in which the gradient is not easy, and then this pseudo gradient can help. And there are many other kind of similar concepts. And one of them is subgradient. So subgradient is a vector G such that this is satisfied. So somehow you also see that it is somehow also related to directions and linear approximations of the function. And a stochastic gradient in which the gradient is a noisy estimate of the true gradient, and these quasi gradients or surrogate gradients. Okay. Yeah, so how to use these pseudo gradients the same way as you do with the gradients. So if you have shown that this is a pseudo gradient, this is a good direction to minimize, then you go into that direction. And one of those is a stochastic gradient. So a stochastic gradient is, the stochasticity comes from this fact. So let's introduce the full program. So let's say that my goal, I'm given a set of points, x, y, y. I'm given these points, many of them. And many can be 10 million points. And then I want to minimize with respect to some weights the sum of over I of the known of 2I minus my prediction. I want to minimize that. But these, so this is my goal function. Then my goal function is f. This is f. And my x, actually, it is f of w. Okay, so my x, that is what I will want to minimize, is with respect to w. To w. And to avoid confusion, let's call my goal function capital F. So this goal function is not the same as my prediction. Okay, but then I want the gradient of f with respect to w. But for computing this gradient, I have to evaluate this function a million times or 10 million times, because I have 10 million points. So computing this gradient is very expensive. What if I take a random subset, or let's say 1,000 points, and I evaluate, so let's say that we have a mean. So let's evaluate this function instead of with 10 million points, with just 1,000 of them. And this 1,000 is random. So this is a noisy version of somehow it is not call it I, let's call it K. So at the iteration K, I have chosen 1,000 points and I evaluate the gradient of this function with respect to the 1,000 points, and not with respect to the 10 millions. Okay? So if these 1,000 points are randomly distributed in the 10 millions, it will be an approximation of the two gradients. So stochastic gradient descent is one of these pseudo gradient algorithms. So it doesn't go in the best gradient descent direction. So they make zigzags, which is something that we wanted to avoid. But at least my evaluations are much cheaper because I'm only using 1,000 points rather than 10 millions. And also there is something very nice because now we know some techniques to avoid zigzags, and we know the ones that we have here, I think, the momentum and the IMS talk, the adaptive step size. So, and now you understand actually this problem is the neural network problem. So normally you have a loss function, very typically this one. You may have many different loss functions, but this is a very common one. So this you understand now why they use this stochastic gradient descent, because you don't have to use the 10 million points. Okay, very good. Then I don't remember if I want to talk about this. I think we can stop here. We can stop here for today, and tomorrow we will continue with more. Any question up to here? No? Okay, so good enough for today.